A uniform block of mass 10 kilograms is released at rest from the top of an incline with length 10 meters and inclination 30 degrees, and slides to the bottom. Consider the following two cases. A. The coefficients of static and kinetic friction are mu s equals mu k equals 0.1. So they're the same and they both equal 0.1. So let's start with this case. So I'm going to start by drawing a free body diagram for this. So here we have the incline. Here's our block. And this angle is 30 degrees, or theta. Down we have the force of gravity, mg. We have the normal force pointing up that opposes the block sinking into the incline. Over here, and pulling it up, we have the force of static friction or the force of kinetic friction, and this depends on whether the block is moving or not, if the block is actually sliding down or not. So the friction must be opposing something, and that is the force of gravity parallel to the inclined surface, and that makes a right angle with the force of gravity perpendicular to the angle's surface. These two form a right triangle. This is the angle theta. So this becomes mg sine theta, and this is mg cosine theta. And these are the two components that you can break the force of gravity down into. And just a quick reminder, the positive y direction is perpendicular to the incline, and the positive x direction is parallel to the incline. So this is a quick reminder. So first we need to figure out whether the block is moving or not. So let's say that the block is stationary. So pretend that the block is stationary for this case. If it is stationary, then only the static friction force is acting. The kinetic friction force only starts when the block actually starts sliding down. So from that, we get that the static friction minus the component of gravity parallel to the incline, mg sine theta, must equal the mass times the acceleration of the block, which is 0. Since if the block is stationary, that means that the acceleration is equal to 0. So we can basically say that the force of static friction is equal to mg sine theta. And that's going to be important later. Actually, I don't need to write it here yet. So. And now, in order for the block to not slip, the force of static friction acting on it must be either less than or equal to the maximum possible static friction. Any more than this value and the block will start to slip and kinetic friction will take over. And the maximum possible static friction is given by the coefficient of static friction times the normal force. And to figure out the normal forces, we simply apply Newton's second law again, this time in the vertical or in the y direction, or the direction perpendicular to the inclines, to the surface of the incline. So we get the normal force minus mg cosine theta, the component of gravity perpendicular to the incline surface, must equal ma, which is 0. Again, the block is stationary. So the normal force is equal to mg cosine theta. And then we can substitute this back in. So from that, we get that the maximum possible static friction is equal to the coefficient of static friction times mg cosine theta. And that's that part. So we know that the force of static friction exerted on the block must be less than or equal to this value. So we just plug everything in. So mg sine theta must be less than or equal to the coefficient of static friction times mg cosine theta. And now, if we plug in all of our values, the mass of 10 kilograms times the gravity of 9.8 times sine of 30, so 30 must be less than or equal to the coefficient of static friction, which is given to be 0.1, times the mass of 10 kilograms times 9.8 gravitational acceleration times the cosine of 30 degrees. And now all we need to do is evaluate these two sides and see if this equation holds true. So once you evaluate, you should get that the frictional static force required to keep the block up in place will be 49 newtons. And that must be less than or equal to, this right side evaluates to 8.5 newtons. And we know that this is not true. So the block will start slipping because the maximum static friction is not enough to stop it from slipping. So in this case, the block is not stationary. So we cannot say that the block is stationary. Instead, we have to think that the block is moving. So if the block is moving or accelerating, rather. So the block must be accelerating. So A is not equal to 0. So in this case, we can do the same thing instead, but with the kinetic friction. The force, kinetic friction, we know that that is equal to the coefficient of kinetic friction times the normal force, which we found earlier to be mg cosine theta. And that is the force of kinetic friction acting on it. And if you remember, the work done by friction is defined as the negative of the frictional force, because the friction force opposes the direction of movement. So the work, and you have to multiply that by the displacement. Work equals a force acting over a certain distance. So the work is equal to minus negative of the coefficient of kinetic friction times mg cosine theta, which is the force of kinetic friction. And that force is acting over a certain distance, which is also given in the problem. It's inclined with length 10 meters. So now we just plug everything in. Let's do minus. The coefficient of kinetic friction is also 0.1. So you can plug that in. Times the mass of 10 kilograms. It's G 9.8. The cosine of 30. And times the length of 10 meters. So now, if you evaluate all these numbers, you should get that the work is equal to about minus 85 joules. So the work is negative 85 joules. And that is the work done by kinetic friction. So in A, the frictional force does negative 85 joules of work. Now we have another case, that's case B. And this one says that the coefficients of static and kinetic friction are mu s equals 0.8 this time, and mu k is also 0.1. And we need to find the energy dissipated due to friction. So if the block actually slips again in case B, then our answer would be the same, of negative 85 joules. But we're not sure of that, so we need to run the numbers again. If you remember from earlier in case A, we said that the force of static friction acting on the block must be less than or equal to the maximum possible static friction. And we calculated that the force of static friction acting on the block is given by mg sine theta. And the maximum possible force was the coefficient of static friction times mg cosine theta. So all we need to do is run this equation again to see if it holds true. And the only thing that's changed is the coefficient of static friction. Everything else stays the same. So we remember that the left side evaluated to 49 newtons, and that must be less than or equal to the maximum static friction, which we need to calculate again. 0.8 times 10 kilograms times 9.8 meters per second squared times the cosine of 30 degrees. So evaluating that, you should get that the maximum possible static frictional force is 68 newtons. So in this case, this equation holds true, and this block will not slide. So in this case, only the static frictional force is acting on it. And if you remember the definition of work to be the force times the displacement, even if we have a force of 49 newtons, the block is not actually moving. It has no displacement since it's staying in place and not sliding down at all. So the static friction, the work done by static friction, is simply equal to 0 joules. The work done by static friction is equal to 0 joules. Let's just specify. And this is always true for static friction, as static friction only acts when the item is not moving and therefore does no work. And this is how you would solve this problem here.